Section 15.3, the rate law, the effect of concentration on reaction rate. So we talked on Tuesday about what a reaction rate is, the change in concentration of one of the species over time. Now we're going to talk about a rate law, and this shows us how the reaction rate is related to the concentration of those reactants. So we're going to look at a very simple reaction. Just one substance is falling apart, decomposing, and making products. So A goes to some products. We don't care what they are. We can write an equation describing the rate in terms of concentration, and this is what is called a rate law. It's just an equation. So the rate is equal to some constant, and we call this the rate constant. So the rate constant times the concentration of A, and again, when we put something in brackets, that means the molarity of that thing. Okay, so it's concentration. Default unit for concentration in this class, always molarity. Default unit for time, seconds. And then that concentration is going to be raised to a power. So that exponent is known as the reaction order. We will be talking about a zero order reaction. That's where n is equal to 0. We'll talk about first order reactions where n is equal to 1, and second order reactions where n is equal to 2. There are other orders possible. We could have n equals 3 or n equals 2/3. I mean, you can even have fractional orders. So let's look at a couple of graphs. Here we're looking at reaction concentration versus time. So we start with a high concentration, and as the reaction proceeds, the concentration of that reactant goes down. That makes sense, right? When n equals 0, that means we're going to get a straight line here, because the rate does not change with the concentration. So we're going to have a straight line, because the slope of this line is the rate of the reaction. For first order, the concentration will be a curve like this, because the reaction slows down as time goes on. And for second order, it's going to curve even more. Over here, we're going to look at the rate versus the reactant concentration. And so, here we have the rate law. So rate of reaction, and this is the concentration of A. Well, for a zero order reaction, that exponent is 0, and anything raised to the 0 power is 1. So here the rate is equal to the rate constant, and so we just see a straight horizontal line. The reaction rate stays the same all the time. First order reaction, the rate is proportional to the concentration. And so if the concentration is 0, the rate will be 0. As the concentration increases, the rate increases. And it's linear. Second order, the rate is proportional to the square of the concentration. And so then we get this exponential curve, right, where it increases faster and faster as the concentration is higher. Any questions? So I have a question: what does the order depend on? We're going to learn about that. It depends on lots of things. But we'll get to how we figure that out very, very soon. Great question. Anybody else? So in a zero order reaction, the rate is independent of the reactant concentration. And this is kind of a weird situation. The example that the book uses is a reaction where you're just having sublimation. You're having a solid go into the gas state, and there we see that the rate is constant. It doesn't depend on concentration. If you have a solid here, how do you measure the concentration of a solid? You can't. Not really. I mean, I suppose you could use the density and find out how many moles per liter are in the solid, but it's just pure substance, right? What happens here is as the reaction goes on and material goes into the gas state and then condenses up here, the amount of material that's available to react is the same because this top layer sublimes and what's underneath? The same number of atoms, right? And so as this disappears, we still have the same amount of reactant available. And that's why the reaction order is 0. It doesn't depend on the concentration. So here we have the amount of reactant available for reaction, that's the important thing, is unaffected by changes in the amount of reactant. First order reaction, the rate is directly proportional to the concentration. This makes a little more sense. We'll talk more about theories of how reactions occur. But you can imagine if you have two things that need to react, in order to react, they have to run into each other, right? It's like, how can you meet someone and fall in love if there's nobody around, right? So if you're in New York City, there's people all over the place. You're probably going to meet somebody interesting sooner than if you go to, say, Wyoming, where the entire state's population is less than Fresno without Clovis, right? They're just like spread out. You can drive for miles and not see anything, right? So it's hard to meet someone, right? Because there's just nobody there to meet. So it's kind of the same with a chemical reaction. The more reactant molecules are there, the faster the reaction is going to occur. So we see that the rate slows down as the reaction proceeds because the reactant concentration is going down. And in a second order reaction, it's just more dependent on the concentration. It's dependent on the square of the concentration. So we see it being even more sensitive to the concentration. Okay, so let's see if we understand that concept. So the same kind of reaction we were just looking at, just one reactant forming products, and we're told that doubling the concentration of A makes the reaction rate double. So what is the order? The reaction rate doubles when the concentration doubles. I hear 1, yes. It was like hearing little mumblings, but nothing clear. 1. So we talked about a 0 order reaction. The rate doesn't depend on the concentration. If we look at the first order rate law, where this has an exponent of 1, and we usually leave the 1s out because they're assumed. The rate is proportional to A. If we double A, we double the rate. Any questions?
So on the 2, what's happening?
On number 2, what's happening? Great question. So reaction order 2, and we've got A squared. So if we double this, then it's going to be 2 squared, and so the rate will quadruple. It'll be times 4. Okay. So whatever the factor by which we change the concentration, you square it, and that's the factor by which the rate changes. Any other questions? Okay, there's Tiger's question. Well, how do we figure out what the reaction order is? You have to do experiments. Can only be determined by experiment. We cannot look at the chemical equation and figure it out. Somebody has to do an experiment for that particular reaction and let everybody else know. Okay. So how do you do that by experiment? One method is called the method of initial rates. And we're going to use this method in experiment 15A, which we're doing not next week, but the following week. So in this method, we take the initial rate of the reaction and we measure it. And we're going to run the reaction several different times with different initial concentrations. So here's some example data. So running the reaction with a concentration of 0.1, we measure the rate, it's this. We change this concentration, we measure the rate again, the rate changed. We do it a third time, measure this again, the rate changed. So we can look at, well, what did I do to the concentration? We're doubling it, right? That's doubling the concentration. And then going from 0.2 to 0.4, again, we double the concentration. So the previous example, we saw that if you double the concentration and the rate doubles, then it would be first order. So let's see what's happening over here with the rate. 0.015 to 0.030. That's doubling also. And some people can see that very easily and other people can't because, your brain is better suited for things not involving numbers, and that's fine. We need you in the world. How do you figure that out? Well, you could take 0.030 and divide by 0.015 on your calculator, and it'll give you a 2. If we go from 0.03 to 0.06, also doubling, right? Because 60 is twice as big as 30. So we double the concentration, we double the rate. What's the reaction order? 1. It's tempting to say 2, and I find myself doing that too because we're talking about doubling. There's 2. And so, reaction order 2. No. It's the same thing happening on both. That's reaction order 1. So the reaction order is 1. So it's first order. And we could write the reaction rate law then. The rate is equal to the rate constant times the concentration of the reactant to the first power. So, if it makes you feel better, write a 1 there. That's fine. Yeah. Right. So for a zero order reaction, if you double the concentration here, the initial rate's going to stay the same. Yeah. And we have to look at the initial rate because as time goes on and the concentration changes, if it's first or second order, the rate is going to go down. So we have to look at the first initial rate because that's the only place where we really know what this concentration is. Okay, and this is determine the rate constant. Well, this is the rate law. We're trying to find K, the rate constant. And here we have data. We have the concentration of A, and we have the initial rate. So we can just pick one of these rows and plug the numbers into this equation. I did the top one yesterday. I'll do the bottom one today. So we're going to look at this last trial. So the rate is 0.060 molarity per second. And that's pretty much always going to be the unit for rate. It's like miles per hour, molarity per second. That's going to equal the rate constant, what we're trying to find, times the concentration, which was 0.40 molar. So then we'll solve this for K. So we take the rate 0.06 and divide by that 0.4. And we get K is equal to 0.15. And what are the units there? Well, we had, actually, let me write this out 0.060 molarity per second divided by 0.40 mole. Yeah, the molarities are going to cancel out. So the number is 0.15, and now what we have up here is 1 over S. So it's 1 over S, or we could also call that S to the minus 1. Kind of a weird unit, but that's what it is per second. Any questions? So here's some sample data for a zero-order reaction. Here we're doubling the reactant concentration, doubling it again, but the rate stays the same, doesn't change. Second order, again with the same concentrations, we're doubling and doubling. So let's just write that down. So this is times 2, and this is times 2. And going from 0.015 to 0.060, that's times 4, right? Again, take 60 and divide by 15 on your calculator, you're going to get 4. And 0.06 to 0.24, also times 4. So here we see that the factor that we're changing the concentration by is 2, and the factor that the rate changes by is 2 squared. Right? 4 is equal to 2 squared. And that's the order right there. Any questions? So, like this data, sometimes you can look at the data and figure out the order without doing much math. Other times it's not so obvious. And then what do? We're going to use this equation here. And that looks kind of complicated, right? There's all these letters and numbers and what are we doing there? Well, I don't know if you remember back in Chem 1A, we did PivNert over PivNert. And doing that, we could derive our own gas laws, whichever ones we wanted, because do we really care about the names? No, we don't. We just need the one we need, right? And so we put 1's up here and 2's down there. And of course, the ideal gas constant is the same, so that cancels out. And now anything that isn't changing cancels out, and what's left is the equation that you need. Okay? Looks kind of complicated. If you get the idea in your head, though, not so bad. Let's see if I can get this to work. We're going to do the same kind of idea here. So rate law, rate is equal to the constant times the concentration raised to a power. So we're going to take one rate law and divide it by another rate law. And this is for the same compound, but at a different concentration, the rate's going to be different. Is the rate constant going to change? We have the word constant in its name. The rate constant is constant, right? So that cancels out. So we need to make the conditions clear, which one is 1 and which one is 2. It really doesn't matter. They put 2 over 1 here because typically the second one is going to be a higher concentration, a higher rate, and this gives us numbers that are larger than 1 instead of fractions. So the rate 2, concentration 2, rate 1, concentration 1. And we'll do an example, I think on the next slide, where we plug some concentrations in and solve for n because it's not obvious. Any questions? So before we do an example using that funny looking equation, let's look at what are the units for the rate constants. Well, you could memorize these, but I don't like memorizing anything extra other than what I need to memorize. Or we can just know the rates. We do need to understand, this is a rate law for 0, 1, and 2, but there's like a nice pattern there, so we can learn that, no problem. How do we figure out the units? Well, what we're going to do is we're going to put the units for rate in over here. So the rate is in molarity per second, and that's equal to the rate constant. And then we're going to put in the units for concentration, which is molarity, but here it's raised to the 0 power. Right? Anything raised to the 0 power is equal to 1. So this is equal to the rate constant. So those are the units for the rate constant of a 0 order reaction. The units on the rate constant are just whatever we need to cancel out the other units. Might seem a little like cheating, but it is what it is. So we can do the same thing for the first order. The rate is in molarity per second. We've got our rate constant, and we've got the molarity of the concentration. So now what we'll do is we'll rearrange. So we've got one of these on each side. We can cancel those out, and the rate constant is going to end up with units of 1 over second, which can also be written s to the minus 1.
So on the rate there, 0 is a constant rate is molarity per second.
Right. So a 0 order reaction, the rate constant has units of molarity per second. First order rate, the rate constant has units of 1 over second, or s to the minus 1 per second. And someone yesterday said, well, could we say that's hertz? Could we say the unit's hertz? Well, you could, because that is what a hertz is. Hertz is something per second. But we never do that. So, there's nothing wrong with it, but it's not helpful for what we're talking about. So, second order rate, again, we're just going to put the units in here. Rate is molarity per second. It's equal to the rate constant times the concentration squared. Well, what are we going to do here? Let's write this all out. So we'll divide by molarity squared here, divide by molarity squared there. When you get these compound fractions, things can go funky in your mind, so let's straighten that out a little bit. That is the same as molarity over seconds times molarity squared. You may think, well, that doesn't look much better. No, it doesn't. But we can take the molarity on the top and cancel one of the molarities on the bottom. So now there's a 1 up here. So here, the rate constant is going to be 1 over molarity seconds. I know, weird unit. Or molarity to the minus 1, s to the minus 1. We will often need to put units on our rate constants because units are really, really important, right? But you don't have to memorize these. If you're solving for the rate constant, have your other units in there and just take care of the units and you'll end up with the correct units. If you're given a rate constant and they say, well, what's the order? You can't identify the order from the units on the rate constant. But, that's only because somebody else did the experiment. Any questions? So reaction A going to B has been determined to be second order. So we know this is second order. And we've got the initial rate here at an initial concentration of 0.1 molar. What is the initial rate at 0.5 molar? So second order, the rate is equal to the rate constant times the concentration squared. So we could do the math and calculate this, or this, being a conceptual question suggests that we could also just kind of think about it, which, some people would rather just do the math, that's fine. But what is the change from 0.1 to 0.5? What is the initial rate multiplied to get the new, concentration? What is this multiplied to get the new concentration? 5. It's multiplied by 5. So if the concentration is changing by times 5, then the rate is changing by times 5 squared, or times 25. So which of these is that initial rate times 25? It's got to be D, right? Because this is a 1 in it, so if you multiply by 25, you're going to get 25 somewhere. Maybe the decimal places, you're like, can't do that this early in the morning. But look, none of the rest of these have 25 in them. So that would be the answer. Any questions about that? Okay, so we've been talking about one reactant. What if you have more than one reactant? Which we often do. Well, we can write a generic reaction, generic chemical equation. So we've got AA plus BB goes to CC plus DD. And here, A, this lowercase a, is the coefficient for the element or compound A, and this lowercase b is the coefficient, right? We mentioned this on Tuesday. So the rate is proportional to the concentration of each reactant raised to some power. So now we have two reactants. So in our rate law, we've got two reactants here. And so we've given one a subscript of M and the other N because they're not necessarily the same. In fact, most of the time they're different. So M could be 1 and N could be 2, or there's so many combinations. So we can talk about the overall order for this reaction, and that's the sum of the exponents. So that would be M plus N. That's the overall order. And how do we figure out what the rate law is? We have to do experiments. When we defined the rate in terms of concentration, change in concentration over change in time, we were able to use these coefficients, right, and just write out equations. These reaction orders, these exponents, are not directly related to any of those coefficients, and so we cannot look at the reaction and say what they are. I just want to emphasize that because there's a part later in this chapter where we're all very tempted to do that, so we're not going to do it. Okay, give the overall order and the order with respect to each reactant. So they're giving us a chemical equation and the rate law. So if we want the overall order, we're not going to look at the chemical equation. It's not going to help us out at all. We're going to look at the rate law. So the overall order is the sum of those exponents, right? So overall is 1 plus 1, which equals 2. And again, here they wrote the 1 because they're trying to point out, yeah, there's a 1 here. Remember, if there's nothing written there, it's an assumed 1. So what's the order with respect to hydrogen? 1. We're just asking, well, what's the exponent on the concentration of hydrogen? It's 1. And with respect to the iodine, also 1. The rate law is what gave us that information. The chemical equation helped us not at all. Okay, let's look at this one. So here's our rate law. What is the overall order? 3. 1 plus 2 equals 3. That's a good kind of math to do before 9 o'clock in the morning. How about the order with respect to hydrogen? 1, because its exponent is 1. And with respect to no, it's 2. Nitrogen monoxide is capital N, capital O. Isn't that yelling? Mm-hmm. I have 6 kids. It's one of my favorite words. It's one of my favorite compounds. No! Any questions? No. Good one. I see what you did there. That's great. Okay, so determining the order and rate constant of a reaction. So this one's going to be a little more complicated than the one we looked at earlier. So here we have our chemical equation. We have 2 reactants. And here we have some data. So we have different concentrations for the first reactant, different concentrations for the second reactant, and the initial rates for each of those combinations. Okay? So we can only look at one thing changing at a time. And so, the person that did this experiment knew what they were doing. Because if we compare row 1 to row 2, well, here, this concentration is changing, but that one is not. By changing just one concentration, we can see how this concentration affects the other one, right? So, going from 0.01 to 0.02 is multiplying by 2, right? So then over here, going from 0.0035 to 0.0069, some of you can do mental math and come up with that. Others are not so good at that, which is fine. Well, let's take 0.0069 and divide by 0.0035, and that gives us 1.97. So does that mean that we have to do something complicated, or could we round that to 2? We can round that to 2. Okay, how do we decide that we could do that? Well, for one thing, we could use significant figures to help us with that. 2 sig figs, 2 sig figs. And if I take that ratio, this should also have 2 significant figures, and to 2 significant figures, it's 2. Why didn't this come out perfectly? Because this was real data, and the measurements have uncertainty in them. It's not going to come out perfect. So we changed this by 2, and this also increased by 2. So what's the order with respect to this reactant? 1. See, it's so tempting. It's first order. So this is first order. Okay. Now we need to find a combination of 2 different rows where the second concentration is changing, but the first one is not. So that'll happen right here. Here, this is the same, and this one is changing times 2. Yeah? Okay, So then let's see what this is over here. And yeah, good luck with that one. 0.0098 divided by 0.0069. 1.42. Ew, that's kind of messy. 1.42, and the next digit is a 0. This is one of those ones where it's not obvious. It's not first order, because they should both be times 2. It's not zero order, because it is changing. It's not second order either. It's something else. Ugh. So we have to do that rate over rate thing. So rate 2, and I'm going to call this row is number 1 for this, and this row is number 2, just so we don't get confused. Rate 2 is equal to the rate constant times the concentration of the first compound. And we figured out what the order of that one was. It was 1. So that concentration, whatever it is, and the second one, oops, not a 1. That's supposed to be a 2. And this is what we don't know. We don't know what that exponent is. And we'll divide that by the same thing, but with subscripts of 1 instead of 2. You kind of have to go back and look at it, make sure you did it correctly. So, in the 2 experiments that we chose, CHCl3 is the same for both, right? So that's going to cancel out. Everybody cool with that? The rate constant isn't changing because it's a constant, so that's going to cancel out. So let's write this without all those things. Rate 2 is equal to the concentration of Cl2 to some power divided by rate 1, which is equal to the concentration of Cl2 in the first condition to some power. We are going to be using exponents and logarithms in this class. And I know some of you, as soon as you finished whatever class you learned that in, you pressed delete and you wiped that out of your brain. That's fine. I can teach you what you need to know for this class, but you have to ask me, because if you don't ask me, I'm going to assume that you know the math, okay? Although I absolutely know that not all of you do, and that's totally cool. In the appendix of the textbook, there's a little section that reviews math properties of logarithms and exponents. What you can do here, because these are raised to the same power, we can group the concentrations inside parentheses and put the exponent on the outside. These are the same quantity. They look different. So we're going to use this part is equal to this part, and we're going to plug the numbers in. So here's rate 2, 0.0098. And I'm going to live dangerously and leave the units off here. heresy. So we're going to take rate 2, divide by rate 1. And that will equal, right, the second concentration, which is 0.020, divided by the first concentration, that quantity raised to the n power. You following? Questions? So let's do the math on those fractions. So we've already done this math, but we could do it again. We got 1.420. So 1.420 is equal to 0.0098 divided by 0.0069. And what's 0.02 divided by 0.01? Is 2. And that is raised to the n power. We're going to use logarithm to get rid of that exponent, to bring it down. Now, you could do trial and error or something, but that's kind of a waste of time. Or I'm going to show you later how you can use the number solver on this calculator. It'll do that for you too. But to get this exponent down, we're going to take the logarithm of both sides. You could use the natural logarithm or the base 10. It's not going to matter here. I'm just going to use the natural log. So the log of this side, 1.420, is equal to the log of 2 to the n. And a power of logarithms is when you have the log of something raised to a power, that is equal to the exponent times the log of the thing. And if you're thinking, oh gosh, how am I going to remember that? You don't have to. We can get the calculator to do all of this for us. But some of you like this stuff, right? Okay, so how do we get n? Well, I'm running out of space. Let's divide both sides by the log of 2. Those cancel out. So n is equal to the log of 1.42 divided by the log of 2. So I'm going to do that on my calculator. 1.42 divided by the log of 2. And I ran out of room. I'm going to go up here. Maybe make this purple. N is equal to 0.50589. The exponents that we're going to have, that we're going to see, will either be whole numbers or nice fractions. We're not going to get 7/16 or something crazy like that. What nice fraction is this really close to? 1/2. Yeah. So n equals 1/2. Why didn't it come out exactly 0.5? Because it's real data, and there's always a little bit of error. Any numbers that we give you in problems, in homework, in lecture, on exams, there's going to be some stuff like this, but it's going to be close. Now, when you do an experiment in lab, because it's the first time doing that experiment and you're still learning, it might come out really, really weird. And then you just have to talk to me and ask me, what should I do with this crazy number? Okay? So now we know what the rate law is. The rate is equal to the rate constant times the first guy to the first power and the second guy to the 1/2 power. So we did A. Any questions about how we got there? So a great thing to do after class sometime today is to look at this problem and try to do it without looking at your notes. If you well, I can't not look at them. Well, go to the lecture video and scroll forward to this slide and then pause it before I start doing the problem. Make sure that you can do this by yourself, okay? So let's use this next slide because that first one now is just a mess. Okay, so there's the rate law we just determined. They want us to find the rate constant. Well, we have all the information we need right here. In fact, we have it times 4. What we need to do is we need to take a rate and each concentration and plug them in here and find out what K is. Okay? Since we haven't used row 4 yet, let's just use that one. If you were doing this experimentally, you would calculate the rate constant for each of these. They're going to be slightly different, and then you would average and report the average. We don't want to take the time for that. So we're going to use row 4, and we're going to plug those numbers in and do the problem. Okay? So the rate, what's the rate? Well, it's over here. 0.027. We are going to do the units here. Molarity per second is equal to the rate constant, which is what we're trying to find, times CHCl3 concentration, 0.040 molar, to the first power. If you want to write a 1 there, go ahead. I don't feel like it. And then we need the chlorine concentration raised to the 1/2 power. So 0.040. Whoops, I forgot the unit. Shame on me. Solve for K. That looks a little icky, doesn't it? In Chem 1A, I kind of hammered into you, always rearrange the equation and then plug the numbers. Take this, solve for K, and then put the numbers in and do the math. That doesn't always work in Chem 1B because some of our equations have logarithms and other things happening, and so that's not necessarily the best way to go. So I'm going to show you how you can use the solver on this calculator to do this. Okay? Okay, so for the YouTube people, we did row 4, and it didn't come out exactly right. So in the recording, I'm going to do row 1, because that's what I usually do. And that gives us the answer that the book gave us. Oops, gotta fix this. It wasn't that it was a wrong answer, but it was slightly different. And they all will be slightly different. And then when you average them up, you're supposed to get an average. And we did all of that, and we got an average of 3.4, which is only a difference in the uncertain digits, so not a problem. But anyway. Okay, so what if you were going to do this without the number solver? What would you do? So what I would do is I would take the 0.0035 and I would divide by 0.01 times 0.01 to the 1/2 power. How do you get a 1/2 power? Well, 1/2 is the same as 0.5, so you can use the X to the box button, or you could use the caret button. So if we do that, 0.0035 divided by 0.01. And people have a lot of trouble with this. Put parentheses around that guy. Divided by 0.01 times 0.01 to the 0.5 equals 3.5. Now what about those units? Turns out there's a mistake in the units of the answer. So the numerator here was molarity per second. And in the denominator, we had molarity times molarity to the 1/2 power. So let's make that into a single fraction. Molarity on top, molarity to the 1/2, and seconds are in the bottom. These cancel out. And the correct unit is 1 over molarity to the 1/2 times second, or molarity to the -1/2 seconds to the -1. So this guy is wrong. I can fix that with my white pen. There we go. That's right. Any questions? Okay, back to a conceptual question. That was kind of some more math than some of you would like. It's okay. So here we're looking at this reaction between oxygen and NO. And the diagrams represent the reaction mixtures in which the number of each type of molecule represents its relative concentration. And they're telling us this is first order for O2 and second order for NO. They're asking us, which of these mixtures has the fastest initial rate? I don't expect this to be immediately obvious to anybody. Let's think about what that rate law would look like. Rate constant times oxygen to what power? 1. Times NO to what power? 2. And it's not because there's a 2 coefficient, it's because they did an experiment and they found it was 2. So which of these concentrations is going to have a bigger influence on the rate? No. Yes, it's no. This is going to have a bigger impact. So what we're looking for down here is something where there's more NO than oxygen. Which one would that be? C. This one has 2 oxygens and 4 NO. This is 4 oxygen and 2 NO, and this is 3 of each. Any questions?